Thanks everyone for being here this afternoon, the opportunity to speak to you on the scintillating topic of vapor intrusion. I know it's an hour after lunch, so it's I know people are kind of, so if you need to take a break and get some coffee, I won't be offended at all. but that's not my fault. Okay, so the three major areas I'm going to talk about today are starting with just a reminder on the VI pathway and how a conceptual model plays into assessing the VI pathway. And a little new thing here when we talk about vapor intrusion, the screening distances and screening concentrations that often come into play when we're assessing vapor intrusion site. A second part of the talk, we'll look at the nuts and bolts of sampling for vapor intrusion and QAQC among those different media there. And then the third part of the talk, I'll look at some of the newer topics related to vapor intrusion, specifically techniques that can potentially address the variability that we're so often faced with when collecting indoor air samples or soil gas samples, and whether we have a representative sample and is that sample good enough to make a final decision on. So we'll look at some of the things that are going on more recently in that area. This table is a table of the new MOA member states VI guidance. This is for your reference. There are the guidance, some of these guidances are more than 10 years old, but I highlighted the Massachusetts and New Jersey guidances as they have the most recent and detailed information on VI data collection methods. So they are good references in that respect because they are the most recent. Okay, the conceptual site model to evaluate the VI pathway. The VI pathway requires three things: a source of VOC vapor, and that doesn't mean a source area, that could be a dissolved phase plume. Second is a mechanism for transport to get the VOCs into the environment where they could get into a structure. And thirdly, we need a receptor, which is an exposure point, and it can be an enclosed space. But that could also be, if you're looking at redevelopment of a site where there may be a new building, a receptor could be a future receptor. So looking at each one of these in turn, just briefly, this is a cartoon from the Mass DEP VI guidance showing the various potential VOC sources to drive vapor intrusion. It includes a VOC containing soil, that is a vadose zone source. It could include VOC containing groundwater, a dissolved phase, or you can have a NAPL situation, which could be present in floating on the water table. That could be a potential driver for vapor intrusion. The transport mechanisms. How do the vapors make it from the subsurface to the to near the foundation of the structure you're concerned with? We start with partitioning, and you look at the dissolved phase. Potential for partitioning from the aqueous phase to the vapor phase near the water table or the capillary fringe. That's the first thing that has to happen for vapor to potentially make it into the vadose zone. Or if you've got a vadose zone source, you're going to get transfer from soil into the gas, where then it could migrate upwards. And that upwards migration through the vadose zone is primarily driven by concentration gradient, a diffusion concentration gradient, until you get near the surface of the foundation or the ground surface, where advection most likely takes over. And advection is the bulk vapor flow driven by pressure gradients. And we most commonly are aware of this through what's called the stack effect. When a building is under, or particularly a residence is being heated, the thermal gradient between the indoors and the outdoors can drive heat to rise, creating a mechanism for the air that's leaving that house to be replaced by the soil vapor. So that advective flow near the foundation is what potentially creates the vapor intrusion issue. But in the VI world, there's also another potential transport mechanism, and that's the preferential pathways. And this is an active area now of a lot of focus. It's a current environmental science and technology certification project, research project funded by the DoD. They're looking more closely at this sewer pathway, either a sanitary sewer or a storm sewer pathway. And the way that this works is that VOC in the headspace of the sewer can migrate back up the laterals that are connected to a structure and then make their way into a home through faulty fixtures, dry traps, or a floor drain in this case. And that can occur from a sewer that may be intersecting a VOC groundwater plume or an apple plume. But there's also the possibility that there may be an industrial facility nearby that's discharging VOCs into the sewer. We've seen this scenario in a couple of places that ends up creating a vapor intrusion problem unrelated to any groundwater contamination in the area. And then there's a more of a question mark around whether a sewer in the vadose zone above the groundwater table, can that actually receive VOCs into its headspace and then act as a preferential pathway. The last section here is about the VOC entry through utility penetrations. These are more traditional preferential pathways we're used to talking about: sumps, elevator pits, penetrations for sewer, water, gas, electric conduits. And I think it's still an open question is whether the backfill around some of these utilities can act as a preferential pathway within the vadose zone. So a lot more, potentially a lot more things to think about when assessing a vapor intrusion situation. So just a quick example of how a conceptual site model was built to rule out the vapor intrusion pathway. In this case, there was an industrial facility with a plume migrating off-site, but through a series of investigations, including multiple and physical chemical lines of evidence, the vapor intrusion pathway was ruled out to the nearby residences. And this was demonstrated through a program that showed that there were downward hydraulic gradients. It was creating more of a diving plume here. That was manifested not just by concentrations that were higher, deeper in the water than at the shallower, but you had this clean water lens over top, along with silt and clay-rich soils and high water saturation near the ground surface. So this was acting as kind of a natural vapor barrier. And then the proof in the pudding was to have some subsurface gas samples collected as well, and that showed non-detect for, in this case, TCE was a contaminant concern. So these multiple lines of evidence were able to converge and demonstrate no VI pathway without the need to go into the people's homes, which can be very disruptive, as you know, to take subslab and indoor air samples. So moving on to screening distances, this is a common approach that's used in most states in the country. And I've shown an example here of what the Massachusetts screening distances are for VOCs in the different types of media, and how far away you have to be from the structure that you're interested in to rule out the VI pathway. These vary from state to state. So you have to be aware of what state you're working in is to apply these screening distances. And the screening distances also go hand in hand with concentration screening values, which is shown on this slide as an example of the VI residential screening values for TCE. Again, the new MOA states listed here along with US EPA's value. And you scan your eyes across this table and you can see for different media here, we're looking at orders of magnitude difference in what the screening values are for different media. And does that mean that one state is better than another? I'm not going to answer that question. But just look at indoor air alone spans an order of magnitude from a low of 0.4 for TCE to Connecticut at 5. And then soil gas, even multiple orders of magnitude difference. And when I refer to soil gas here, I'm primarily referring to subslab soil gas, as most states have a preference for subslab soil gas sampling over exterior soil gas sampling. But there is still some value in exterior soil gas sampling, even though many states are guiding us to try to take samples from the subslab. And the reason for that is because subslab samples are closer to the potential point of exposure. They perhaps represent the potential for exposure closer to where you're going to be measuring indoor air. Okay, so moving on now to the nuts and bolts. Starting with exterior soil gas, we'll look at temporary and permanent probe installations. Subslab vapor, same thing. And then lastly, we'll look at indoor air. So exterior soil gas sampling. There are several advantages to undertaking an exterior soil gas sampling program. This can be particularly valuable when you're getting into an initial assessment of a release in a neighborhood with a residential scenario, and you want to have a better understanding of how many homes might be affected. A soil gas sampling program can help narrow things down, so you're just not kind of going out there into the neighborhood and knocking on the door and asking to come in and drill a hole in their floor and take a sample in their house. There's some rational basis to do that, and soil gas sampling can help narrow that focus. It's, as I said there, it's less disruptive than interior sampling. And ultimately, you may have to do that interior sampling, but if you can have some more information and more context to support that, it can be valuable. It also can be done, exterior soil gas sampling, concurrent with some soil profiling. So you can look for some of those natural vapor barrier features, like a fine-grained material that might be saturated, that could help build multiple lines of evidence for not having the pathway complete. On the other hand, most states favor subslab vapor sampling, as I mentioned earlier. The other thing here is that you're getting a sample, basically a grab sample in space and time, and is that sample subject to natural spatial and temporal variability? Probably is, but that doesn't mean it's not. There's no value to it. And then lastly, you could miss those preferential pathways that we referred to earlier. So how do you go about collecting exterior soil gas sampling probes? Well, if you're looking at a one-time sampling event, it's part of maybe an initial characterization. A common thing to do is to use either hand-driven tools or hydraulic push tools, and I have an example here of, I think this is a GeoProbe post-run tubing system, where you drive a hollow rod with an expendable dry point to the depth you're interested in, using, in this case, a slide hammer. And then the point is knocked off, and the tubing is threaded down in through the hollow rod, and then that tubing can be connected to either your Suma can or to a peristaltic pump, where you can extract the vapor into a Tedlar bag, for example, if you're just interested in screening level type data. And this can be done again either by hand or by machine. But there's also potentially a good reason to put in permanent exterior soil gas monitoring points. This may come into play when you know you're in for a longer term monitoring situation of the soil gas situation, or you have a remediation, an SVE remediation system, for example, and you want to monitor the progress of the vadose zone cleanup. You can go back to these points again and again, not just to get samples, but also to monitor the vacuum in the vadose zone. So this is an example of a nested soil gas monitoring setup. The 3 probes across a bedrock situation here, and they're constructed with 6-inch long, 6-inch long stainless steel screen connected to 1/4-inch riser, and they're all in the same core hole here. And then you build this up as a layer cake with a sand around the implant and bentonite above the top, and then natural material above that. And so you get this, you have the ability here to monitor soil gas over multiple levels. This is a pretty intense soil gas monitoring program here. A permanent probe can be as simple as just one of these things at the depth that you're interested in. So moving on to subslab port construction, permanent installations are also beneficial too, especially if you're talking about a mitigated structure where you need to go back and monitor a pressure field extension, a vacuum field under the slab. You have a permanent installation you can go back to and do that from. So typically involves drilling a hole through the slab and installing some hardware, preferably stainless steel hardware if it's a permanent installation, that then you can connect your sampling equipment to. And I have some photos of how this is done. So one of the most useful tools in the VI world is the hammer drill. No one should be doing VI investigations without one. So you're drilling through the slab. Make sure you're doing utility clearance before you do that. And then you're inserting your hardware. This is a kind of a swage lock setup, compression fittings. And nice thing about this is they could be set flush with the slab, and with some this is Porrock, I believe, that allows you to have a nice clean flush surface there. And if you're doing it in carpeted areas, you can punch a hole through the carpet and cover that hole with the carpet circle later on. And if you just don't want to get involved with building your own subslab ports, there are commercial products available. This is the vapor pin, but it's installed the same way that this other port is installed. So moving on to sampling these things, this is a typical setup of sampling from a subslab port using a Summa canister setup. In this case, there's a field duplicate going on at the same time. And now I'll just take a look at maybe one of the first QAQC measures that is commonly recommended for both subslab and exterior soil gas sampling, and that's integrity or leak testing of the port construction. So the idea here is to assess whether during the sampling process, are you getting any dilution of your subsurface vapor by introduction of ambient air from the surface. So a common way to assess this is to inject a tracer just above the port. In this case, it's ultra high purity helium being injected into a shroud over the port. And then as you're withdrawing soil vapor from that port, the tubing is passing through an environment of helium. And if there's any leaks, their helium is going to be introduced into the sampling train and into the Tedlar bag that you have here. And then you can screen this with a helium meter, and you have information right away of whether your port construction is sound. There are other tracers that can be used, but typically a lot of the times you have to send those off to the lab to have them analyzed. The benefit of having the helium here and a helium detector is you have the real-time information to decide if your port is good. There's other simpler ways to do this. This is involving water, and there's actually a whole list of these different methods, I believe, in the Mass VI guidance, if not the New Jersey VI guidance. So for more information on that, I would consult those documents. Okay, so many times in residential scenario, we're just going in there one time to grab a subslab sample. It's a similar thing. You're drilling the hole through the basement floor or the lowest level floor, but instead of constructing a port, you're just snaking your tube down through that annulus that you've just drilled, and you just need a temporary seal, and you're going to fill that hole back up with grout when you're done. We found that hot beeswax works pretty well. It actually works very well to get a good seal there, and other things are possible to use, modeling clay, for example, but you want to make sure you're not using anything that might have VOCs in it that would cross-contaminate your sample. And we know beeswax doesn't. Okay, so how many subslab samples do you need to collect in a residential scenario? It depends on what state you're in. I've got a cross-section here of different states and what their recommendations are for the number of subslab samples. It's typically around 2. And there's not usually much said about how many times you have to do this. I think the conventional thinking is you're going to go and do this once. But Massachusetts actually references 1 to 2 events. And I guess it all depends on what you find. If there's nothing there, that may be better evidence that you might be able to stop there. But again, the multiple lines of evidence idea comes into play to support how many times you do something like a subslab sampling. For larger or commercial industrial buildings, there's some guidance from New Jersey Department of Environment Protection about how many samples to collect based on the square footage. But this is kind of arbitrary because really how many samples you collect should depend on the foundation construction of the building. And if you've got a building that's been built on multiple times over the years with lots of subgrade structures, and you follow this guidance, you might be missing a completely isolated area that could be a potential source. So the caveat here is to use some professional judgment to determine the number of subslab samples. But it's a place to start. So there's a lot on this table, and Jennifer mentioned, all these slides are available on the website, so you can go back and look at these in more detail. But this is intended to summarize some of the major QAQC considerations for subslab and soil gas sampling. They're the same, pretty much the same either way. Sources of error and bias, the QAQC measures associated with them, and some of the lessons learned. And we talked about one of the main potential sources of error and bias is to get a diluted sample as a result of a leaky surface seal. A rule of thumb here is to maintain your sampling rate at less than 200 milliliters per minute. Again, somewhat of an arbitrary number, but generally consensus is that's a flow rate that's not going to create a over vacuum condition or an under pressurized condition, which can drive ambient air to either into your port construction or into your sampling train. If you're looking, another possibility is leaky tube fittings. So you want to use gas tight fittings for this, no quick connect fittings. There's actually a shut-in test procedure. Again, the New Jersey guidance has a good photo and a step-by-step description on how to conduct a shut-in test. Basically, put your sampling train under vacuum and make sure the vacuum doesn't decrease. You want to be aware of, be careful with VOCs reacting or absorbing or desorbing from your tubing. So the standard practice is to use either stainless steel or Teflon tubing for this type of sampling. Maybe an exception here is if you're doing using a peristaltic pump to get screening samples from a subslab port or an exterior soil gas. You're going to have that silicone tubing in the peristaltic pump, but the chances of that being a problem are low compared to the purpose of what you're doing that sampling for. Filling a Tedlar bag to get a screening sample, it's not a big deal. Which brings us to Tedlar bags, and you want to be careful using these because they may contain VOCs just by dint of how they are manufactured, and they also allow VOCs to diffuse in and out of them. So if you're going to use them, you probably want to use them with an on-site laboratory, have that capability to analyze them as quickly as possible. These are not typically sampled and then sent off to a lab for analysis because the potential loss of accuracy is pretty high. And then for SUMA canisters, this is how you would normally collect a subslab sample or an exterior soil gas sample. There's a whole nother table on that we'll get to shortly. So moving on to indoor air sampling, these are the typical state guidelines, pretty much things that are well recognized that should be considered in conducting an indoor air sampling program. It kind of starts with a pre-sampling survey, which we'll talk about on the next slide. The common way to do this is use the stainless steel pre-evacuated canisters, also known as SUMA, which is kind of like the Kleenex of a pre-evacuated canister. Just say SUMA all the time, but it's actually a registered trademark. Third bullet there is if you're going into a home or a site for the first time, particularly Massachusetts calls this out in their VI guidance, they recommend the full TO15 analyte list, unless there's justification for narrowing the list. I know lots of clients that would just roll over when they hear this is not good news. So because you really end up potentially having to explain all those compounds and why they're there. So the work you can do up front as part of your exterior work, your site conceptual model, anything you can do to narrow down that list is going to be money well spent, because you're potentially, once you get into homes, as we'll talk about later, anything goes and potentially what you can find. Conventional practices for indoor air in residences is 24-hour average time samples, where when you're in a commercial industrial space or an occupant, a place where people are working, 8 hours is also typically accepted in most states. You want to collect at least one sample from the lowest level, the basement or the level that's closest to the ground surface, and one sample from the lowest living level if that's not the basement. And then many states, of course, want you to do concurrent subslab and indoor air sampling, but what you should be doing here is collecting your subslab sample after you collect your indoor air sample. so you don't have cross-contamination of subslab vapor into indoor air as a result of drilling that hole through the slab. So on the first day, set up your SUMA canister, come back the next day, 24 hours, finish up that sample, and then do your subslab sampling at that point. So potential errors and bias. Indoor air sampling is fraught with potential error and bias, and that's main reason why a lot of states recommend subslab sampling, because that is at least an initial filter on looking at whether the compounds you detect in indoor air are also detected in the subslab vapor. But the air can move both ways. It can go from the soil into the house or from the structure into the ground. It depends on what the pressure gradients are. But the indoor air sources of VOCs are listed here. There's a lot of them, including in commercial industrial spaces, the potential for building materials, building fabrics to contain VOCs that could be confounding to determining whether it's a vapor intrusion problem. So some of the QAQC measures to take to try to limit the potential for this uncertainty about where your indoor air VOCs are coming from. The pre-sampling survey is a common recommendation in the various VI guidances, but this really needs to be done a number of days in advance if you're going to have a chance to get that material out of there and have the air turn over inside the structure sufficiently so that there isn't a residual here. If you've got high levels of PCE in a residence and 24 hours later you do your sampling, there's still a pretty good chance there's going to be residual PCE after you remove the source. So if you're going to be going into a home, take advantage of that time to do some interior VOC screening with some sort of field instrument, because you can get some real-time information on what might be causing the issue you ultimately see in a SUMA canister. A couple of other points here at the bottom to consider as well. So this is a similar table to the previous one, focused on SUMA canisters, and this goes for all media, anything you're collecting a SUMA canister with, soil, subslab vapor, or indoor air. The labs aren't going to want to hear it, but one source of potential error or bias is contaminated canisters. Canisters are reused over and over and over again. They go from one site to another site to another site, and the labs have great procedures to decon them, but there's usually a choice between getting batch certification of cleanliness or individual certification of cleanliness. Highly recommend getting individually certified clean canisters and obtaining the lab QAQC report to document that the cans you received are free of the VOCs that you're going to be looking for. We sometimes run into faulty equipment. The flow controllers, the device that controls how long a sample you're getting, the 8-hour or the 24-hour flow controller, those are often, I would say often, they can be faulty, and you find out halfway through your sample that you're just about at the end of the vacuum and you haven't got to 4 hours yet. So having some backup controllers on hand can be beneficial. And there's some other things here that I'll maybe one last thing here. You want to make sure, this is common practice, to close off your canister with some residual vacuum in it, record that vacuum on the chain, and then the lab can compare that when they receive it, so you make sure there hasn't been any leakage during shipment back to the laboratory. And that would be another source of potential bias. So how many indoor air samples to collect? This is the age-old question, and we're going back to the question of 24-hour samples. What does a 24-hour sample get you? What are you trying to measure? Are you trying to measure the long-term average in that structure? Are you trying to measure the worst-case scenario? The 24-hour sample probably doesn't get you either one of those. But we forge ahead, and we still come up with at least some starting points. And this is a cross section from the NUMOA members, what they recommend for how many indoor air samples to collect. And you can see it spans from one round in the heating season in New Hampshire to multiple rounds across several heating seasons in New York. So clear lack of consensus on how many samples to collect. Maine is at least more specific in saying that to close out the site, you need 4 4 successive clean rounds spaced 3 months apart to conclude there's no VI pathway. All right, so back to this question of variability of indoor air sampling results. You may be familiar with the Arizona State University Research House out in Utah, also known as Sun Devil Manor. It's been a highly instrumented house for a long time, and they've been collecting indoor air data there continuously. And this is a period of 2 years, TCE concentrations on the y-axis. And you can see this pattern of very noisy data, but with some general spikes over the winter time. But if you're interested in what the maximum potential indoor air concentration is, you have a very high likelihood of missing that, depending on when you sample, although the best chance to get it is to sample in the winter time. And we'll come back to that in a second. But the point is, a 24-hour sample represents neither the worst case nor the neither the worst case short-term or the long-term average. This is an industrial facility, again, continuously monitored over about 2 weeks. And you can see the fluctuations here in PCE and indoor air that actually tied into the operations of the HVAC system. So again, going in here and taking an 8-hour sample, if this is a 3-shift operation, you may be missing peaks here that are occurring when the HVAC system is being turned down overnight. So now I'm going to, last part of the talk, just move on to some of the newer methods to perhaps address some of this temporal variability. And there isn't any one answer to this question, and it's still an active area of research, which we'll look at here as well. But one approach would be to use long-term passive samples. This kind of potentially gets to the answer of what is the long-term average concentration. If you want to know that question, answer to that question, the passive samplers could be your way to go. Here's some examples of what they look like. Their advantages are they're small, easy to use, easy to ship, typically cost less than SUMA canisters, and they can provide up to 30 days or more a composite sample that can answer that question of what your long-term average is. On the downside, you have to be careful about selecting the type of sampler you're going to use along with what compounds you're analyzing for. You can't get one sampler to do the whole TO15 list. You have to match your sampler with the compounds you're interested in, as well as the detection limits that you're interested in. So this takes a little bit of work consulting with the laboratory to pick the correct sampler. It may miss short-term concentration peaks, but that's the name of the game with passive samplers. But that you can do something about that, as I'll show next. It doesn't mean there's nothing to say about short-term concentrations. You can still use a passive sampler to figure out, at least theoretically, what your peak might be, and that's here on this slide. So you can come up with the theoretical daily peak concentration from a passive sampler by multiplying the passive result, say it was 1 microgram per cubic meter, that's the long-term average, by the number of days of deployment. So that would be 14, your maximum concentration on any given day. If you got a passive result, a 14-day passive sample result, would be 14. And both of these samples have the same long-term average. 1 is 1, and 13 days of 0, and 114 is also an average 14-day concentration of 1. So you can use this formula to potentially calculate what your, if you're looking at TCE, what your daily max threshold could be. If you're interested in not going over 6 micrograms per cubic meter and you collect a 14-day passive sample, you have to be less than 0.43 micrograms per cubic meter to ensure that on any given day you didn't go over 6. It's a simple concept, but it's interesting that you can still use a passive sample to say something about what the peaks might be. And if you're interested in this, there's a couple of guidance documents out there that have a lot of information and detail to follow up on, the EPA engineering issue paper and the ESTCP document. Real-time monitoring, very, very powerful in assessing temporal variability of indoor air concentrations. Some examples of some of the instrumentation that's used. Hapsite might be one of the more familiar ones. The Frog 5000 is also an instrument that's out there that can be used for real-time monitoring. This is the gas chromatograph ECD. Hartman Environmental Geosciences offers this. It's a instrument that can be set up and achieve very low levels to the levels we're interested in for risk assessment for most of the compounds we're interested in. You get your results very fast. You can set this up so you can sample multiple locations in a structure. So you run tubing out to the different locations you're interested in, and this device will cycle through those and give you real-time results. And you can look at that data in real time through the internet through a company that offers some software that goes with it. You can also use it as a mobile lab and bring grab samples over to it and have the instrument analyze those right on site. An example of a deployment of this device, it's set up here in an open office in a building that was undergoing the startup of a subslab depressurization system. So in real time, you're able to get information on the indoor air concentrations at multiple locations throughout the building. And it was nice to see that once the SSD system started up, the indoor air concentrations flatlined to non-detect. But it's interesting to see what was happening before the SSD system was started up. You can see the variability among these 4 locations in these 4 graphs here. And one feature that kind of stands out is this peak common to all locations. That turned out to be what was actually a snowstorm that occurred, where the snow built up against the air intake of the HVAC unit and blocked the air coming into the building. And over the weekend, that snow gradually melted and more air was brought into the structure and diluted the concentrations, and eventually kind of returned to what the baseline level was before the SSD system started up. And then once that happened, everything went down. So on the Hapsite, advantages here, it can detect very low levels of VOCs. It's portable, it's excellent for sleuthing, moving around a building on a cart, doing some crime scene investigation type stuff, looking for sources of VOCs coming into your building. Gives you results very quickly. On the downside, it has, depending on who you get this from, it has some issues with functional reliability. And it requires some special training experience. It's not as simple as using a PID. The instrument needs to be calibrated. It should be checked daily. It's calibration checks on a daily basis, which means you have to have a standard gas available that you can check the readings against. And its accuracy for certain compounds, in our experience, it's been a little more difficult to rely on for breakdown products of PCE and TCE. But very reliable for PCE and TCE, and many times that's what we're starting with. So you can take this around and figure out what's going on very quickly. This is a large building subject to TCE vapor intrusion. This instrument was capable in 2 days of getting 75 samples all over the building, establishing what the baseline conditions were within 2 days, and figuring out where the vapor intrusion was coming from, looking at the VOC entry pathways, and figuring all that out in a very rapid period of time. I wanted to make you aware of another real-time instrument that's available, particularly for the state folks that are here. This is the US EPA Trace Atmospheric Gas Analyzer, also known as TAGA. Dave McCunis from EPA gave a presentation on this a couple weeks ago. It's archived now on Cluin if you're interested in it. A few snapshots from his presentation. It provides even finer grain detail on indoor air concentrations. And you can move around just like you can with the Hapsite and get real-time information. If you're interested in this, you can contact Dave. I think it's primarily available to state-led or EPA-led type projects. I'm not sure third parties can hire them out, but for the state folks here, it's something that could be available to you. So the last topic here is guided sampling. How might we come up with a better strategy to select a time to get an indoor air sample that has a chance of representing what might be the worst case situation? This is an active area of research right now. So I don't have any final answers, and there's more to come on this. But this is that same plot from Sun Devil Manor, looking at indoor air concentrations over a 2-year period. But in addition to the TCE concentrations, also plotted here are the indoor-outdoor temperature differentials at the same over the same time. And you can see that there's at least a visual correlation that when the indoor-outdoor temperature differential is great, that's when you have higher indoor air concentrations for TCE. So this may suggest that temperature differential could be an indicator. We use this now grossly by saying, let's sample in the heating season. But that alone doesn't guarantee you're going to get a worst case sample. It actually may be that you have to have a really high temperature differential for that to happen. This is just one house, so we can't make blanket conclusions based on one house, but it's a start of looking at this a little more closely. And the question we're trying to figure out is, how should indoor air sampling programs be designed to determine the reasonable maximum exposure? And EPA defines that as something between the 90th percentile and 98th percentile, typically the 95th percentile of the universe of concentrations that could occur in that particular house. It's supposed to quantitatively represent the worst case, but not the long-term average. Unfortunately, the 24-hour average is still our standard, but again, it neither represents the worst case nor the long-term average. So we're kind of in this middle ground with 24-hour average samples, and we're doing our best to kind of guide ourselves to sample in the heating season to have a better chance of capturing what might be a worst case scenario. So the question on the table is, can statistical methods be used to guide sampling a little more rigorously? This is the same Sun Devil Manor data, again, plotted a different way. It's the TCE concentration on the y-axis and temperature differential on the x-axis. And you can see that when temperature differential is highest, where the TCE concentration is highest, these are the 95th percentile lines. This one is for TCE, and the yellow one is for temperature. So sampling indoor air when you have a temperature differential above the 95th percentile gives you a 34% chance of capturing the 95th percentile of the TCE concentration. So 34% is not great, but it's better than nothing, it's better than zero, and better than random perhaps. So it's at least the first step. This is radon plotted the same way. So if you collect your indoor air sample when radon is above its 95th percentile, then you have a 40% chance of also capturing the highest TCE concentration. So it's very early at looking at this, but so far what can be said, maybe the obvious thing to say, is that it's not a good idea, at least in residential structures, to sample when indoor-outdoor temperature differential is not great, or when radon is not present above, say, the average level. So at least that gives us some initial guidance. On the downside, if we're going to adopt this kind of approach, we might have to set up monitoring of temperature radon ahead of time so that we can get in and do the sampling. So it's still to be seen where this goes, but there's more information to come on it. And one last thing I wanted to mention, based on the statistical analysis done so far, there is some suggestion, at least based on the Sun Devil Manor data set, that if you collect 3 winter samples, same winter but on different days, spaced apart at least a few weeks, so you're getting independent samples, 3 wintertime samples, and calculate the 95% upper confidence level of the mean of those samples, that is equivalent to the 95th percentile of the distribution of TCE that could be in that structure. So it's equivalent to looking at a reasonable maximum exposure. So maybe there's some promise here that we can perhaps just, it remains to be seen. We have to see how this plays out, but there's some suggestion, at least statistically, that 3 independent wintertime samples, calculating the 95 UCL on that, could be a way to look at what your reasonable maximum worst case scenario could be. So So there's actually a presentation coming up, a workshop at AEHS in a couple of weeks here at UMass, led by Henry Schuver, and they're going to spend a number of hours going through this whole topic if you're interested in. So here are my wrap-up messages, starting with the working conceptual site model. Definitely an iterative process, and if you're going to rule out the VI pathway, you're going to need multiple lines of evidence. Screening distances and values are common ways to do that. We talked about all the different ways to sample soil gas and indoor air. There are good, well-established procedures available to do that, particularly in the Massachusetts and the New Jersey guidance documents. But don't forget the real-time analytical tools. They can really speed things along and get you where you need to go much quicker than the traditional collect your subslab and indoor air samples. And then just the active area of research. Stay tuned here to figure out if there's better ways to address this confounding issue of temporal variability, especially when talking about indoor air sampling. So thank you very much.
Great. Any questions on vapor intrusion? Got one.
Hey Dave, have you done any work once the Subslab systems have been installed, whether it's the standard heat pressurization systems, VI systems, they were pretty clear with the higher vacuums, that you've seen systems fail if you documented good vacuums across buildings and residences? You've seen data that would say maybe we shouldn't feel as confident that these systems are doing the job 100% of the time?
Repeat the question.
The question is whether we've seen data that would suggest that subslab depressurization systems may fail over time.
They don't hold up.
Periodically fail, don't hold up.
Most agencies are feeling very confident.
Yeah.
And once they're in, you're good to go.
Yeah.
And of course, we rely on that. You know, our data too.
Yeah, we do. My personal experience is I haven't had failures of SSD systems, but at the same time, we're also at least doing annual checks of the operation, the pressure field extension, the fan. So walking away from these is not what I would recommend. I think you have to have at least some monitoring and maintenance program. That doesn't mean you have to do sampling, but this is an engineering control, and engineering controls, particularly if they're mechanical, they can fail. So checking on that mechanical reliability is a good idea.
Okay, anything else for Dave? All right.